Hey everybody, welcome to our March version of the Chill Zone, where Don Gillis condenses the facts of working with Opteon low GWP refrigerants. My name is Chris Piles, and I'm going to be joining Don today just to help out. I want to thank each of you guys for jumping on. We know that your time is valuable, and we're honored that you chose to spend about an hour with us today. Now, the transition to lower GWP refrigerants is here, and now is the time to get ready for all of your customers' questions. So really, that's the main point of what we're doing here, right? We want to empower you guys with the information so that when you're asked the question, you've got the answer. Let's see. If you do have any questions, if you want Don to go over something, or if you want to just check back on something, feel free to type your question into the box down at the bottom of the screen. And what we're going to do is we're going to spend some good quality time making sure that these questions are getting read and getting responded to right here. Okay. Now let's see. We're also going to have a few questions of our own, quizzing you on the material that we put through. We just kind of want to double check and make sure that the information is getting across. And this might be your first time here, or you may be a regular, but either way, grab a coffee, sit back, and take some notes as Don Gillis compresses the juicy info into your head. All right, take it away, Don.
Thank you, Chris. That was good. You can tell we're getting experience. We're kind of getting cocky now. So very good, man. Hey, welcome everyone. And as Chris said, thanks for joining us today. Really a treat here. And anytime you have questions, like Chris mentioned, put in the chat if you have some idea. But let's get started. We're going to revisit something that we've done already prior to early in when everyone was still kind of getting to know the 454B and the flammability and all that good stuff. So we're going to touch on a few things here. Oops. I think everybody knows me, so I'm not really going to go. To condense this real quick, 33 years ago, I started in the industry. I was a laid-off factory worker, went to work for a mom-and-pop's Lennox dealership just down the road from where I live. First year was nothing but cleaning up job sites and carrying somebody else's tools. And then, like we all do, we move up the ladder. I eventually became a journeyman, and I held a service manager's role for about 8.5 years for a pretty high volume place. I'm still licensed and so on and so forth, but enough about me. A closer look at 454B is going to be the topic. We're going to talk about 454B specifically today and compare it to 410A and R32. And we threw some different slides in this time to give you some different visuals, if you will, on some pressures, temperatures, and those kind of things, and some fundamental stuff too that we're going to work on. So I know everyone's, there's always somebody new starting in the career or their position. So hopefully you can take something away from this. For those of you that've been in the industry for a very, very long time, just bear with us on some of the stuff, and I'll go over that right now. Okay, so up until this A2L or 2L flammability came along, we only had 3 classifications. We had a 1 non-flammable, that's a non-flammable, and then we had 2 flammable, and then we had a 3 that was highly flammable. So the example for 1 would be like stuff we're using already, legacies like 410A and those kind of things. 2 example would be, as it's in brackets there, 152A. You don't see it in refrigerant a lot, but it is out there, okay? And then 3rd is the propane butane, okay? I specifically left 2L out because it's the new kid on the block, if you will. If you were to draw, it was so close to what we're using, the classification 1, that they had to make a new classification. So this 2L classification, the flammability part of it, has been on the face of the earth, the whole planet, for less than 10 years. Okay, that's how new it is, all right? So if you were to make an imaginary line between, let's say, 2L and 2L resembles more what we are using now than it does even a 2. In fact, if you drew this line here, everything to the right of the line, the burning velocity or the speed at which it travels is greater than 10 centimeters per second. On the left-hand side of the line, it's less than 10 centimeters per second. And when it comes to 454B, for example, I'll just use that example, it's like 5.2 centimeters per second. Now in imperial inches, it'd be like 3.2 or 3, somewhere thereabouts. I think you did the math not long ago. So, and fun fact, if you're ever out there on a quiz show or you're taking a test, that is the purpose for this L. They didn't make it a 1.5, they made it a 2L. That L stands for exactly what we're talking about. That has to do with the speed at which the flame travels, velocity, Okay, that L is low velocity. You'll hear it called mildly flammable or low flame propagation if you're fancy and you like to get down in the weeds, but that's what it's standing for if you ever get asked that, okay? So how do they test it, Don? So it's done by a third party. It's the ASTM, and this is the test for E681. And this test example is just for flammability, okay? ASHRAE does two things in standard 34. They do the toxicity, which is the letter, and then they also do the flammability, but they're the ones that call the shots, but it's done by a third party, so it's unbiased, even though we have these facilities up at headquarters, and most people do, most all OEMs do, because they don't want to get, for lack of better words, egg on their face if they send it in and it fails, okay? So what they do here is, and I've been in the labs up at the headquarters up there in Delaware too, and saw them outside the chambers in their lab coats, and they do actually still look like that. They've got their computers outside, and what they do is they introduce refrigerant mixed with air in a closed flask or a tube, if you will, and they've got a stirring mechanism here at the bottom, and it blends this for about 15 seconds. So they're looking on the computer for the perfect ratio to where it hits LFL. LFL is lower flame limit. You've ever seen LFL on data plates and what have you. That means until it hits LFL, it's not even flammable. In other words, too much air or too much refrigerant, okay? It has to be perfect, and each chemical, like propane and A2L, is completely different. This takes a little bit of R290 as opposed to a lot more of the A2L refrigerants, okay? So there's a larger window for the propane to actually ignite as opposed to A2Ls, all right? So this is what we've been using our whole life, our career. A1, this is our comfort zone. As long as it stays in that 90 degree, or V as in Victor, we're good to go. That's a good day, stamp it, move along, let's go, okay? This in fact is 410A. So when we see that little flicker or that lazy flame, if you will, when we're repairing stuff after the line's open, a lot of us think that's oil, including me, but that's actually residual refrigerant, okay? So even though this was very close, if it breaks that line or that 90 degrees, it's considered a flammable refrigerant. And this is how close it was. This is your 2L, the new kid on the block, less than 10 years on the face of the earth and very new to the States, okay? So it broke this line, and that goalpost or that V has a lot of science in it. It's a formula that you use for flammability, and don't ask me to explain it because I tried to understand it myself, but just know this, it's been in place for a very long time when they test flammability, all right? So they've got it down to a science. If it breaks that line, it is then considered flammability, and they don't move the goalpost because that's the way it's been for the beginning of time since they've been testing this, okay? So to give you a visual here, I don't have a picture of an A2, but an A2 would be a lot closer to the 9 and 3 o'clock position. The point I'm trying to make is what we're using now compared to what this A2L is pretty darn close. Now I want you to respect it. You're going to see some new installation, good practice. What used to be good practice now going to be required, and those kind of things from ASHRAE. So pay attention, okay? If you were already using good practices, you're going to be really far ahead of the game, okay? But here's where we want to make sure you're aware of, because you know as well as I do, you're probably all giggling. It's not as bad as it was, but there's still a lot of people out there thinking that there's propane in A2L refrigerants. And the problem is when you say flammability, or somebody does a webinar or anything like that, or you have a book has A2Ls and A3s in it, for lack of better definition, I'm going to show the cornfield boy of me. It muddies the water, if you will, okay? So flammability isn't flammability, as you can tell. 1, 2L, and 3, big difference. This is a much more exciting day at the lab, by the way, when you have the R290. Hey, it's time for a poll question. That came up on me quick.
I did speed up. All right, folks, the L in 2L stands for, and please select one. Is it the heat of combustion? Is it the velocity? Is it the toxicity of the refrigerant? Or is it all of the above? Again, we're talking about just the letter L in the 2L, right? Okay. Heat of combustion, velocity, or toxicity? Pick a question and toss it on in. Right now, I can tell you, oh, Mr. Don, you've done a great job. 92% of respondents are saying B, velocity.
Well, I've got mixed emotions about that. I'm glad I did a good job. It shows me two things. People were listening, but secondly, I really soft tossed that one. I forgot what that question was going to be. So I didn't want to hammer it that hard, but I'm glad they got something out of it. That's good.
Nice.
All right, let's continue on. Great job, gang. So if we didn't add propane to it, Don, what the heck did we do? Oh, there was nothing added that was flammable. It was actually what was taken out of it. So half of 410A, as you probably heard, is R32. The other half is R125. And the R125, for me, this goes back to my prior job, is, fun fact, R32 runs hot by itself, just a little warm. That's not a bad thing. It just runs a little warmer, okay? So R125 was put in there. The two biggest reasons was to keep the discharge line cooler, but more importantly, to keep it non-flammable, because R125 is found in almost every fire extinguisher made. And the way that works is when it's exposed to air, it immediately sucks all the oxygen out where you can't have a flame. So, but unfortunately, the R125 is, in the EPA's eyes, the bad stuff. Okay, so when we made 454B, we went from the global warming potential, GWP, from 2088 to 466. And what they did was they didn't change a lot. They removed the R125. They went from 50% R32 to 68.9. And then they circled back around with this 1234YF, which is a commercial product. And that's underneath the hood of your car. And it's been in the hood of the car for any new car, or if you bought a used car that's been made in the last 8 years, it's underneath the hood of your car, 1234YF. A lot of people ask me, they go, oh man, I'm glad you gave that class. You say 1234YF. I've been saying 1, 2, 3, 4. It doesn't matter, but it's 1234YF. And again, smaller charge. It's underneath the hood of your car. And you know, we got our families in there, so there's nothing to worry about. The global warming potential for 1234YF, if you care to know, is less than 4. You might want to lock that away just in case there's a question, because sometimes I don't remember what the questions were. So that's what it is. So look at this. I mean, just quick math would look, you're right around 1600, but the fact that they bumped this up to 68 from 50%, let's just say, for the sake of not arguing, you lost about 1400 GWP, let's say, of just making the discharge line cool and making it non-flammable. And when you compare an A1 and to an A2L, you saw how close the flames looked alike. So let's look at 454B. First of all, it meets regulatory requirements. It's not ozone depletion. It has a GWP of 466, which, by the way, if you did not know this, as of the 1st of this year, OEMs cannot make comfort cooling systems anymore that are higher than 700 GWP. So we came in way lower than that threshold. It's mildly flammable, yes, and it's close performance, almost identical to 410A. And I'll even show you, we're really going to get down into it to look at these closely. Compatible, commonly used with POE oil. So it is actually the same POE oil as 410A. And here's the ratio again, 31 to 68. No propane, 1234IF and R32. So let's look how close it resembles, because these are the things I get asked. I'm actually out doing training right now on the road. I'm in a conference room right now down in Florida. I just got done giving training to a very large class. Let's look at this. This is the kind of stuff that boots on the ground and the technicians are asking. If you're working from a counter or a branch or a distributor, you get these questions all the time. I mean, I really relied on people at the counter, the distributors. And I mean that sincerely. They were kind of our knowledge. You know, if you didn't get to go to training very often, they were the ones to tell you, hey, we got training coming up, or, you know, hey, yeah, let me look that up. Somebody just came in with that question again. So very, very similar pressure temperature. You can see it over here. Here's the pressure. Here's the temperature, or saturation temperature. This is a saturation curve, okay, which simply means it's your gauges, because we're reading pressures and temperatures, right? Those temperatures are saturation temperature. The low sides are evaporator. The high side's the condenser, right? Similar thermodynamic properties, also similar material compatibility. What do you mean by that, Don? Well, we've already had R32 in 410A, and we've already had 1234YF underneath the hood of your car, and plus 448A and 449 also have 1234YF as part of their blends. So we know it plays well with others. In other words, it's not going to eat copper up. It's not going to eat aluminum up. It's not going to chew up the windings. So we already know it's very similar. When it comes to 410A and 454B, POE oil, identical, POE 32. Now don't think because I'm telling you the pressures and temperatures are the same and the POE oil's identical that you can put the 454B in existing system. You cannot. Okay, first of all, you're going to be breaking the law. It's not designed for an A2L equipment. Plus, you're going to have a different pressure drop no matter how close you are. Okay, so we just don't want to do that. Similar system, and I put DX over there, so it's still going to walk like a duck, talk like a duck, act like a duck. Okay, what I mean by that is it's still the same system with a sensor in there, a refrigerant sniffer. That's all the difference. It's going to be the same thing. All right. And here's just some added bonuses, just between moving from 410A to 454B, if you care to know if it's ever on a test, that's a 78% reduction in GWP. That's where we really shine at. That's what the EPA likes. We're going to be going to all these new refrigerants with a lower GWP, still getting the good capacity out of there, still getting the good COP, or the coefficient of performance, but we're lowering that GWP. Unfortunately, it's a give and take sometimes as far as flammability. You give up something and you get something else. So we got below the GWP, but we had to remove the R-125. But what does it look like on a PT chart? So I took a screenshot of my phone, as you probably remember. I don't know how new this is. It used to be gauges here, but just know this. I got somebody's PT chart. I put 454B in there, and I took a screenshot of my phone, and I put 119 on the low side, because when I put 119 in at 410A, 454B, and also R32, they were real close. Okay, and what I mean by that is, from my experience, on a normal operating system, on a good running system, not always, but most of the time, you're going to see a SST or suction saturation temperature on your low side around 40 to 45 degrees, at least in my experience. Okay, not sketched in stone by no means, but that's, for the sake of not arguing, that's what we're going to say. So when I chose 119 over here on my PT chart, I came across, these are all applications in the same application. You're going to see 40.3 on 410A, you're going to see 45.5 on 454B, and you're going to see 39.2 on R32. And as we all do, whether we're salespeople, trainers, or marketing people, we want to be very transparent about this, because we do sell R32 also. So we want you to be have the most weapons you can, if you will, to go to battle. And I mean that sincerely as an educator. You're going to see both of them. I don't have a slide for this, but if you didn't know, you don't know, because sometimes I assume everybody knows what I know or Chris knows, because that's the world we live in. But all OEMs, with the exception of Daikin, have went with 454B. Okay, so anything Daikin owns, Daikin, Amana, Goodman, will have R32. Now, it gets a little different when you get into chillers. Some people are, the size of the chiller and things like that, and mini splits also. Mini splits, we really thought that was going to be all R32, because most of that's Asian driven. We get that from, the Asian market, if you will. But what we pleasantly surprised to find out was about 60% of the mini split market is going to be R-454B, which surprised all of us internally, quite honestly. And about 40% of that is R32, the last I checked, the last I heard. So you're going to see both of them. We want to make it fair and show both of them, good, bad, or otherwise. Okay. So as I said before, the DX system, the TEV, the TXV, the EEV, whatever you're using as a metering device, it's still going to act the same. You're still going to have the same thing. Nothing's going to change when you walk up there with your gauges. It's still going to be, if you're not even really going to know you're dealing with anything differently, to be honest with you, because really, an HFO molecule or an HFO blend, it's almost like an HFC refrigerant in disguise, and it really is. It just breaks up faster. So saturation is still going to be saturation. We define saturation by liquid and vapor in connection with each other. Okay, you can have one drop of liquid with 99% of vapor, that is saturated, or vice versa. As long as there's a drop of refrigerant in your tank, that's saturation. Subcooled is a little different. Subcooled we're going to find in our liquid line, and subcooled by definition is any heat removed from a liquid below its saturation temperature. So if the saturation temperature is 40, it's and you're reading 39, you have 1 degree of subcooling. We usually take subcooling where? Leaving the condenser or entering the meter device. Superheat is a vapor. We find that in our suction line. It's also found in the discharge line, but it's a higher pressure superheated vapor. But focused on the suction line, this is where we get our superheat. Now, opposite of subcooling, it's a vapor, not a liquid, but it's also heat added to the vapor as it leaves the evaporator. So above that saturated, hence the name superheated, okay? Because now it's picked up all that heat from the load and it's moved by that saturation temperature. So let's take a look at this on a PT chart, okay? And I actually put the actual numbers in here, 454B, and at 115, okay, I've got showing here on my saturation, and I'm reading with my fancy little detector here, 43.7. And when I went to the PT chart and looked up what 115 should be, 454B, pardon me, that was a hard one, it showed me 43.7. So the moral of this story is that refrigerant, hence the bubbles, vapor bubbles or liquid bubbles, whatever mixed, is saturated, okay? Because that's what it's reading, saturation. When we do subcooling or superheat, as you all know, we're just subtracting from what saturation is, right? Okay, where will we find saturation? We'll find it in our evaporators and our condensers, so our coils. And if you're doing a larger system, you'll find it in the receivers, okay? It's saturated there also in the receivers, okay? So we're taking this through the evaporator, for example. We're heat movers. That's what we do. We're moving heat. That's all we're doing, okay? We got that liquid in there, 75%, 50%, then 25%, and we're absorbing that heat coming through, okay? Let's talk about superheated vapor. Now we're going to find superheated refrigerant on the suction side, the larger line, right? And when I went to 454B and I looked up 118, I was even able to put those little numbers in that gauge. I was pretty proud of myself. So 118 showed me 45 degrees, okay, on the PT chart. But my line says 55 degrees, leaving the evaporator, right? Because any heat added to your saturation temperature that's a vapor is in fact superheat, okay? So leaving there, I got a higher number leaving the evaporator at 55, and it's 45 inside the evaporator, so I have 10 degrees of superheat. Easy enough. Where will we find superheat? We're gonna find it here, and if one of the OEMs calls you, I always tell students, and I've been saying this for years, if you're talking to somebody that designed the equipment, whatever brand you use, and they say, hey, what's your superheat? This is the superheat they're referring to, because they want to know if that bulb is reacting, the TXV is matching the load or load matching, okay? Whether it's an EV or a TEV or TXV, whatever you want to call it. And the way that works is, we all know there's refrigerant in that bulb. Most of the time, it's the same refrigerant inside the system, not always. And it's not interacting with the refrigerant in the system, but it's the same concept. The warmer it gets, pressure temperature relationship, the higher the pressure, it pushes pressure down in that hole, which pushes on the diaphragm that then causes, hey, I need some more juice here, okay? Now, if you're talking to a compressor manufacturer, they're gonna probably ask, they want to know total superheat and entering the compressor, because that's their baby, okay? So there's superheat here, and that superheat there, obviously, you know, is going to be higher than this back here. You're going to pick up some superheat, even though this line's insulated. But if it's ripped in an unconditioned space, you're going to pick up more of that. And then you have this superheat here. This is high pressure superheat in our discharge line. And because it's higher pressure, it's much hotter, right? You know what it feels like if you've ever touched a discharge line. It hurts. So let's talk about subcooling. And the example here is I have a 396 PSIG on my gauges on the high side or the liquid side, okay? And it's subcooling. When I went to the PT chart, it said I had 120, okay? But my line temperature, oops, there's a mistake right there. That should be 109, I'm sorry. It is 109. And when I subtract, remember, it's any heat removed from a liquid from its saturation temperature. That's subcooling. I got 109, that's 11 degrees of subcooling, okay? Sorry about that mistake, gang, I do apologize. I think I was doing 404A at one time or something. But anyways, so this is what it is. Any heat subtracted from the liquid below its saturation is your subcooling. So 109, leaving the condenser, okay? This is in the condenser. all right, leaving the condenser or entering the meter device, anywhere on the liquid lines where you're going to find subcooled liquid. In fact, here it is. Now, you know, most compressor manufacturers are going to say take your pressure temperature within 6 inches of each other, especially on a large system when you get into refrigeration, okay? And typically they'll have apertures, if you will, or some way to take your pressure up here closer if it's like a 300-foot line or whatever. But in residential, light commercial, you usually don't have that luxury, okay? Cost is everything, right? But in residential, especially, you don't usually have a big difference between subcooling here to here, unless the line's pinched. If you have a big difference, then we need to start figuring out why. Was the line reduced? Is it kinked or whatever? So on a 35-foot, 50-foot line set, these all should almost be identical. But why would I want to check my subcooling there? Well, because the TXV, that's what it's focused on. When you have a TXV, subcooling then comes into command. Where when we had fixed orifices or a piston or a capillary tube, that was a fixed orifice. That was superheat. That was more, we depended on superheat. But this here is subcooling. That's the reason for the bulb, okay? It activates like that. We know that, okay? So we want to make sure if this isn't a full column, if you will, of liquid, all right, we have issues. You're going to have an inefficient system. If it's somehow flashing off and it's saturated, if you will, or there's bubbles there incoming into the TXV, then that's no good. So by checking this subcooling here, we have then proven with the refrigerant that we're using that we are good to go, okay? So you may have to go down a basement, you may have to go to the mechanical room. I like checking both of them if you have access to the TXV, all right? Now to bring it all together, we've got our saturation here, we've got our superheated vapor, we get climbing up there, and this is what happens. So we're using primarily saturation. Why are we using liquid? Why did we have to change all these states? Why did we have to raise the pressure and lower the pressure? Well, people much smarter than I am, before iPhones or computers even, they figured out the physics of this. When we drop the pressure, we drop the temperature. And all around God's green earth, high pressure goes to low pressure and hot goes to cold. And hot's kind of an opinion, so warm goes to cooler, let's say it that way. And if you're into IAQ, wet goes to dry. And that's physics. That's the second law of thermodynamics, very simply put, okay? So the heat from the load, whether it's residential or commercial, it's coming through, all right? And this saturation that's coming through, 75% liquid, 50% liquid, 25% liquid, it's picking up that heat. We're not really making anything cold, we're removing the heat. And that liquid is a good transfer of heat. We found, or the chemists found out, that the engineers years ago, the scientists, that heat moves heat a lot better than vapor does. You know, I always give the example, if you're outside for 24 hours in air, vapor, okay, you could live at 60-degree temperature. Now, you might be uncomfortable, but you can live. Now, in 60-degree water, let's just say up to your neck, you don't have to even be swimming or exhausted or anything like that. Just in 60-degree water, you will not live for 24 hours. In fact, could be minutes, could be hours, depending on your body mass. It will suck the heat right out of you. So that's what they understood a long time ago before you and I were around, okay? So we're actually picking up that heat, and we call it boiling off, or the saturation temperature starts to boil off as it picks up this load, okay? It's starting to boil off and flash off. And the idea of it is to boil off and be all vapor. The only reason, if anyone ever asks you, if you don't know, and I'm sure 99% of you know, if not all of you, the only reason we have superheated vapor is because we don't want to hear crunchy noises down there on our compressor, okay? Because they understood a long time ago, if they get liquid in here, we're going to slug the compressor, but really it turns into a hydraulic pump, and it's not designed to do that. So we come down here, we take our heat out of there, we're moving that heat down here through the suction line, and the first job of that refrigerant is to cool the motor. 99.999% of the compressors out there are refrigerant cooled. Very few anymore, semi-hermetic are air cooled, okay? So it picks up that heat from the motor, and then it compresses it. And what they understood years ago, way long time ago, is they understood when they compress these things under a magnifying glass, these molecules, that they start moving really fast. So when they moved fast, they got hotter, and they got a higher pressure, hot pressure temperature relationship, okay? So they compress it, it gets really hot. If you ever touch the top of a scroll, you know what I'm talking about. You don't normally do it twice. So right about where that weld mark is on a scroll, that separates low side to high side, if you will. Low suction, high pressure over here, okay? And that now that is superheated vapor above it, okay? And it's a higher temperature, higher pressure. And then we're gonna take it in, go inside the outdoor condenser, comes in the side. We have a fan up here and we're rejecting that heat. But what kind of heat are we rejecting? There's a lot going on there. We're rejecting the heat from the load. We're rejecting our superheat. We're rejecting the heat from the motor, and we're rejecting the heat from the discharge also. So there's a lot going on there that we're discharging. Hence the reason we call it de-superheating. When we come down here, by the way, it's going to enter the coil on the outside from the top because vapor is lighter than liquid. And this is all by design. Okay. And as it starts to eject that heat, okay, it will then go back to its normal form because normal form of refrigerant is a liquid, right? It goes to vapor by changing the state. So it's condensing back here, and now we got all liquid going back. And we're doing that simply because we need to change state back and forth. This is our high pressure, this is our lower pressure. We come back down to this, to our liquid line, okay? And if you ever want to check this, what's cool about this, if you're new to the industry, the condensing temperature is going to be higher than the outside ambient. Years ago, when 10 SEER equipment was the highest SEER rating, which was a big deal back then. I remember going to 10 SEER from 8 SEER. That was a big deal. Okay, we had a lot of rules of thumbs because we didn't have smartphones, we didn't have computers, we didn't have the fun things we have today. We didn't have YouTube, that kind of thing. So you had to do your math. But one thing I really like that still holds true today is you could about bet your bottom dollar, whatever ambient was, your condensing temperature on your high side of your gauges was about 30 degrees higher. So in other words, if it was 80 degrees outside, you were seeing about 110 saturation temperature on this side. And it was like science. I mean, it was almost exact, if not perfect every time, okay? Even though we have a fan out here that's rejecting heat, we're counting on the second law of thermodynamics. Hot wants to go to cold. So it helps reject it out there, okay? So if you don't have that temperature higher, you don't feel any heat blowing off that fan. That's what a lot of technicians used to do years ago before we had all this digital stuff. They take their hand and stick it over the fan. Are we rejecting heat? If it was really hot, you knew you were moving some heat out of there, okay? So we come down here to the liquid side, and then we come back to our TXV, or as I call it, our pressure dropper. Because when we drop the pressure, we drop the temperature. And again, going back to God's green earth, hot goes to cold. It's absorbing that. So they understood that long time ago. It'd be a great world if we just kept this liquid all the way around here, like a glycol system, or if it was all vapor. But we understand DX systems. We had to do this to move the heat design, and we still use it today, right? And it's going to be the same way with A2Ls. And this is just a little fun picture on heat pumps versus a cooling cycle. We have our reversing valve in there, okay? And basically all we're doing is reversing, just hence the name. We name components for what they do, right? Condenser condenses, the evaporator evaporates, and the reversing valve just reverses the refrigerant. So you can see on an air conditioning cycle how this is moving. We're coming in from the discharge line. We're rejecting the heat outside where we don't want it. We're taking it from inside. We're coming back into the expansion valve, and then we're coming back in the indoor coil. Okay, this is low pressure inside the house. All right, and coming back down, bringing it just like I showed you earlier on a heat pump. As most of you know, I'm sure all of you know this, but I have a heat pump at home, and I also have natural gas. So I got what they call a hybrid system. I think I put it in my own home about, guys, probably going on about 16 years ago now. So I got the best of both worlds. So this is how it works. It reverses. Okay, it's either O or B, B as in boy, or O, orange, on your reversing valve. Most OEMs use B as the reversing valve on your thermostat, or O, pardon me, and some people use B. B is only one. I believe that's Rheem, if I'm not mistaken. I know it is. Rheem and Root and everything, Weather King, or their contractor grade or whatever. But it slides over. It says I'm in heating mode now, and it just changes the direction of it. So now we're picking up heat from the outside the condenser, okay, bringing it back, and then we're putting that heat back into the building. You think even though it's as cold as it outside, you couldn't do that, but it is. As long as there's a difference, as long as there's still some heat outside in that for our condensing temperature, it absorbs that and picks it up and puts that heat back in there, okay? It may not be sometimes, years ago, especially when heat pumps weren't designed like they are now, now they really get down low, right? Years ago, you might had to have supplemental heat, which is electric strips basically. And where I'm at right now, that's all they use down here in Florida, right? Anything in the southern states. But where I'm at, you see a lot of fossil fuel, propane and natural gas, okay? All right. Hey, it's time for the pizza party drawing.
It is time.
I do not have the right slide in there, Chris. I got you. I
Hey,
am
that's
so
all right.
sorry. I actually had
This
the slide
this
made up and
gets
everything.
everybody the idea, right? So each month we pick we pick a new winner. And let me see, let's go back. I know last month in February we selected Mike Tipton out of Johnstone Supply. So congratulations for that. I hope it was a great pizza party. And this week we plugged in all the attendees into our random name selector. We came out with Mr. Rick Nelson from Bell Simons up in New England. So congratulations, Rick. You're this month's winner.
Yay. Congratulations, Rick. And I'm sorry, Chris, and everyone else out there. I literally have this slide already made up and everything. I must have hid the wrong one. I do apologize. I actually had January and February up there, and I do apologize, gang. Anyways, congratulations.
Sounds good. Yeah, congratulations, Rick. So you're going to get an email from me just basically outlining what we're looking for. Again, there's going to be 4 pizzas from a pizzeria of your choice, wherever you're at. We're going to send you a box of swag, and we're going to send you a cool Opteon polo shirt, which even us Opteon employees don't get. So it's a pretty cool little gift for you. So I'll be in touch, okay, Rick?
Yeah, which we petitioned.
We petitioned.
Chris and I did. We're disgruntled. We have a grievance box. So congratulations again, Chris. All right, guys, let's move along, guys and gals. Let's look at the performance of 410A, 454B, and R32. What do they look like compared to each other, okay? You might be really surprised here. Again, this is going to look like the same system for the most part. You're going to see some red caps on the equipment. Some signs are going to be there. There's going to be more decals and things like that. It's going to be shouting at you that it has A2L in it. We're not going to put the new refrigerant in the existing systems. Remember that. After I show you this information, I'm not encouraging you or saying, hey, it'll work there. It will not. Okay. Looks like we have a poll question already.
Alive. All right, guys. The poll question is: the R-454B pressures are slightly higher than 410A. Please select one, either true or please press false. So 410AB, are the pressures higher or lower than 410A? If you guys remember, we went from R22 to 410, and everyone thought they were going to lose an eye or they're going to get their ear cut off if there's a leak. Now we're going through another change, and the pressure is changing. Is it going to be higher or is it going to be lower than 410A? All righty. Oh, we've got almost an even split, Mr. Gillis. 50% say true, 50% say false. It's right on the line. What's it going to be?
Dang it. That's a bummer. Yeah, that might have been my fault. I thought we had some gauges up there in the PT chart and everything. So that's okay. What is the answer?
Me?
Actually, I'll tell you what the answer is.
Yeah.
The answer, the 454B will be slightly lower. Okay, it's going to be right around 10 pounds. Should have probably got maybe another slide in there. So I think I may even be showing it here shortly, even more in depth. But just so you know, if you're seeing, like, let's say the high side of 410A, 430, you're going to see about somewhere around 420 or somewhere thereabouts. It's about a 10, 12 degree drop in pressure straight across the board for 454B. R32 is going to be a little closer to 410A, but not quite as high. Okay, so just so you know, it's actually on the high side, 32 will be higher than 410A. So just so you know, again, 32 runs a little warmer. There's a pressure temperature relationship there. So, and that's not necessarily a bad thing. So, so now you know. Okay, the 454B will be lower pressure. So there's, like Chris was saying earlier, unlike when we went from 22 to 410A, and quite honestly, I was a little scared of it. I mean, I came out of that training class that day going, I'm not putting that stuff in my truck. You were already used to those pressures. In fact, they're going to be slightly lower. So there's nothing to fear here. All right, so here we're looking at, actually, probably should have this slide before that question. So capacities. This is the same exact system. 160, On 410A, you would see 155 on 454B. So somewhere around 5. It depends on what the application is and each one of those, whether it's a split system or a rooftop unit, but you get the gist of it. Slightly within 5 pounds lower on the BTUs. Okay, this when 155, we've done this. I've done it off line, and what you're seeing there, it's less capacity. It works out to be about 2% less. Okay, 174 for R32, it really shines there. This is where 454B really looks good. The higher the COP, the more efficient the system is. And when you start with the COP, as I told the class this morning, I did here at the branch where I'm at, COP is a fancy way. It's a coefficient of performance. But what does that mean to you and I, technicians in the field? We're putting out fires, if you will. We got to get Mrs. Jones some cooling. You know, it's hot in the house. The baby's hot. We don't really think about things like COP, but this is the main starting point. When I was at Copeland, this is what all the conversations about. So we're really focused on COP, and this has more to do with the SEER rating or the EER. And basically, what it is it's coefficient performance. If you pull it back and take out all the formulas included, COP is this. Simply put, this is the Don Gillis version. It's how much capacity you're getting out of your evaporator compared to how much energy you're using on the compressor or the system as a whole. So both capacity and the energy you're using comes in combination with each other. And whatever that number is, that's your COP. And the higher that number is, as I said earlier, the more efficient the system is as a whole. Okay. And if I didn't mention that earlier, I think I already did. All OEMs, with the exception of Daikin, are going with 454B. Okay. When it comes to suction pressures, here's what I really want to talk about: 130 to 117 to 133. R32 again is just a little higher, and 117 is going to be a little lower than the 130 on the 410A. On the high side, 419, you're going to see about 395 on the 454B, and then 430 on the R32. Discharge temperatures, if you're seeing 167, 6 inches out from the compressor on the discharge line, you're going to see 177. Remember, we removed the R125, that fire extinguisher, made it non-flammable, but it also kept that R32 cool. Now, R32 straight up is going to be 195. And if you ever take any compressor classes, you know we're getting up close to that 225. So we want to be careful there, okay? When it comes to relatively mass flow, so we have two different AHRI looks at, B and A. So here we have 82 Fahrenheit ambient, so outside air, and here we have 95 When we compare 410A to 454B, when we talk about refrigerant, relative capacity means whenever you see relative in front of anything, that means baseline. So whatever you're comparing to, that's 100%. Okay. So when you're referring to the baseline, or we're comparing it to 410A, then we're comparing it to what it is. It's either a plus or minus. And I said 2%. Let's say, for the sake of not arguing, it's 3%. 3% capacity here, okay? In a higher ambient, we're 100%, and here's where that 2% comes in. So like I said earlier, it depends on the application or the ambient temperatures. Relative COP, again, relative, anytime you see the word relative in front of anything, that means that whatever you're comparing to, that's utopia. That's baseline. That's 100%. When it comes to COP, we're about 1% higher on the 454B. And when we get into the higher ambient temperatures, 95 degrees or above, you're seeing a 3% COP. So that's huge. That means the system is humming down the road. It's really efficient. Mass flow, if it's 100, you're going to see 78 on the 454B, and the same thing in the higher ambient temperatures. Discharge line, 145 here and 149 here. 154 to 165. So it's going to go up slightly. Again, we don't have the R125 in there. Okay. By the way, advantages to a lower mass flow, lower energy consumption. That's why your COP is higher, and it's a stable system operation. A lower mass flow can help maintain stable temperature and pressure, preventing excessive wear on the components. Okay. And there's a give and take there. So this is something I put in here for you that I used to use at my prior job. This is what we used to call curve charts. We used to drive around with these way long time ago when we were talking with walkie-talkies in our trucks, even before cell phones and even pagers. We would have this binder in the back behind our driver's seat. And each one of these pages were color coded. If you're old like me, I just turned 62, you're probably giggling about this. Or if you're young, you're probably going, what prehistoric era was this guy from? So the pages would be colored to match the refrigerant tank. And every refrigerant had these tanks because we didn't have the smartphones and those things, kind of things. And basically now they're called curve charts. And it's basically, this is your evaporator temperature up here. Here's your condensing temperature on the side. So you can take your condensing temperature at 130, and this refrigerant we're comparing here to is what? This is 410A. Okay, so it's a ZP38 Copeland compressor, 410A. Okay, and we're running 477 on the high side. It's showing us a condensing temperature on our high side as 130. Okay, on the low side, we're seeing about 45 saturation inside the evaporator, dead center, midpoint, if you will. You're going to see about 130 on the low side as far as the pressures. And when we bring those together with our fingers here, we should be seeing everything here. The C stands for the capacity, and it's showing us at this temperature and this pressure, which it's designed for, we should be getting 38,000 BTU out of there. Well, hence below, look at that. It's a ZP38. So we are right in the sweet spot of what they call the envelope, okay? Anything outside the envelope, if we were to lower our temperature or pressure on the evaporator, we would lose capacity. And the same thing over here, we would get more capacity, but then other things would change. You don't have to be right inside the dead center, but this is what the target is. This is dead center of the target. This is what they're shooting for, okay? The C is the capacity. The power or the watts is the 36. The A is your amps or your current, okay? And then we go into mass flow, EER, BTUs, and the isotropic, always have trouble enunciating that name, efficiency, which just means the energy you're getting into your compressor. It's the energy of the compressor, all right? So that's what that looks like. So let's talk about glide. Not a big conversation here with 454B or 410A. We don't really use glide to use the dew and the bubble point. And as you know, dew is used for superheat, bubble is used for subcooling, and glide, you only have glide when you have a blended refrigerant. And blended refrigerant is defined by 2 components or more. So it could be 2, could be 4, could be 5, okay? But it's the difference in the boiling points. Okay, that's what it's difference in. Different boiling points in the blends, boil off at different times, and that's what the glide is. When it comes to the POE oil, 32, 32, and then we're going to use 46 for R32 because, again, it runs a little warmer. So just like an automobile or a truck, 10W30 or 5W30, you know, like motor oil is, you're going to need a higher viscosity oil if something runs hotter because of the friction, basically. When it comes to the GWP, remember I said the cap is 700 as of the 1st of this year. You cannot make air conditioning equipment higher than 700 or above. And 2088 was 410A, 466 for 454B, and 676 for R32. Okay. Myth versus fact. If a leak occurs, the service tech will need to remove the entire charge and make the necessary repairs to recharge a system. The fact is, no. It is classified as zeotropic, and it does have a glide of about 1.4. Now, before you say, hey, my book says 1.8 or whatever, it changes whether you're in heat pump mode or air conditioning mode, okay? And again, that glide is the difference between the boiling points. That's all it is. In refrigeration, we see more of it because then it gets up in the 6s and the 7s and the 9s. And if you're working with 407C, excuse me, it's like a 12-degree split on that. So the point I'm trying to say is you can top off 454B just like you could top off 410A. That's the takeaway from this, okay? So if you lose a little charge 5 years down the road, yes, you can top it off. But if you're going out knowingly topping off even a 410A system every year or twice a year or whatever that looks like, the moral of this story, you will eventually start to lose capacity because you'll start to lose what they call fractionation. But it takes it takes about 3 or 4 top-offs to even lose 1%. But fractionation is a real thing. It's the same as it was with 410A, but it is very hard to do. The moral of the story that I like to tell, fix your leaks. If you know when they have a leak, fix the darn leak, okay? You won't have that issue. So nothing's changing from 410A to 454B. When it comes to R32, it's a single component, so it doesn't matter. Now, myth versus fact on 454B, it's a drop-in for 410A. That is a fact. 454B is not a drop-in replacement for 410A. In fact, our 454B or any A2L refrigerant will only be used in A2L equipment. There is, I don't even like the term drop-in, retrofit. Okay, there is no retrofit gas for 410A at this time, and we don't foresee that happening. Okay. Myth for fact, all service trucks techs must be recertified. That is not true. All service techs that hold an EPA Section 608 certification will be grandfathered in just like you were with 410A and will not need to take an additional exam. Do we recommend training, A2L training? Absolutely. That's why I'm out here right now. That's why our whole training team, everyone that's out there, whether it's webinar or in person, is training you to get you educated on A2Ls. It's no different than when we taught when I went and took my test for 410A. It wasn't connected to my EPA card, but they were asking, wholesalers were asking you to get certified for it. But moving forward on your EPA exams, whoever comes in behind you, they will start seeing A2L questions just like we did with 410A, okay? Myth or fact, when replacing an existing residential or commercial central 5-ton split system, you must replace the refrigerant lines. That is a myth, okay? As long as the line sizes are the same as the new equipment, 454B compared to 410A, you can use the existing lines, okay? Same copper, the material, nothing's changing there. But if it was undersized before, then it's going to be undersized again, or vice versa if it was oversized. So guarantee, check, and make sure the line sets match the new equipment, okay? If you were cleaning up the refrigerant lines with some kind of flush, keep doing it the way you were doing it. If you were cleaning up old school, like I like to do with nitrogen, like the compressor manufacturers like you do with nitrogen, you keep doing that. If you're really high end and you like those guns that shoot the little plugs down them and clean them, which I think are just cool as heck. I'm not going to name drop here, but keep doing it that way. What I'm saying is nothing's changing, okay? I'm not telling you one way or the other. Whatever you were doing before with 410A, you're going to keep doing with 454B or R32, okay? The cleanup's the same. There's no different there. Now, when we get into the commercial charging, when we start talking about that, there's going to be some added things to it, and that gets into marking the line sets. If they go into like a slab or some place it's unconditioned and you can't see the line set anymore, you have to put some red tape or a red identifier. And we'll get into that at a later webinar with ASHRAE. 15 is commercial and 15.2 is residential, okay? We're going to talk about our resources now. We're almost at the end. We got another poll question. Chris?
All right. And that last poll question of the day, R32 and R410A have the same POE oil. Is this true or is this false? Don talked a bunch about the POE oils that are used in 410A and 454B and R32. The question is, does R32 use the same POE oil as 410A, or does it have a different one? All righty, as we're watching the votes coming on in, about 50% of the people have selected, and we're looking at about 73% are saying that it's false. Different POE oil.
That is correct. Anybody, do they have access to the chat, I'm assuming, Chris?
Yeah, they do have access to the chat and also to questions.
I don't know if we have anything to send them or give them, except that a boy will mention your name. Does anybody remember the POE for R32?
Oh, man.
Or 410A? And if you don't, that's okay.
I'm watching to see the chat boxes.
Nobody? That's okay. No problem. It's POE 32 for 454B and 410A. It's POE 46 for R32. Remember that higher viscosity, a little thicker oil, because R32 naturally runs a little warmer, okay? Just a fun fact, not a bad thing. Just like cars, like I said, change the engine size or whatever, depending on what that looks like, you need a higher viscosity oil.
All right, and Tom did comment that it was POE 46, so great job, Tom.
Nice. Wow, Tom, that a boy. I got to get some kind of sound effect. I need a bell or a horn or something to go off, Chris. Congratulations, Tom. Send us your email or something, and maybe we'll send you something, a little something, just kind of off the wall, maybe a PT chart or something, or I'll email you some good stuff. Maybe, who knows? I'll see what I got. We'll come up with something. Good job, Tom. Thanks for remembering that. So here's just, we're at the end here. We're going to show you our website and those kind of good things. And we're going to take our Q&A. This is just a trifold. So for those of you that working from a distributor or store a lot of refrigerant as a contractor, big companies, national companies, this is a trifold that you can get for free. You can go to this link here. It looks complicated, but the way I like to do it, because I like the easy button, just put in the Google machine AHRI A2L storage. Just put it in just like that, AHRI A2L storage, and it will come up first. And it looks just like this. And that's how we made this PowerPoint. Literally, that PDF went right on this PowerPoint. So it tells you the shelving, how far you can stack, how the distance is. So it's really, really cool. It shows you all the good stuff. This is actually the form right here. So it's right in detail. Now, this is not being all the way enforced. Chris, you correct me if I'm wrong. The way I understand this is the guideline moving forward. It's just not put in place yet at all the municipalities, or it's gotten down to the local jurisdictions where, you know, when they do fire inspections, that kind of thing. But this is going to be the guideline on it moving forward. Okay, so everybody's on the same page. All right. Here's our website. Plenty of stuff in here. Tech tips, Chemours refrigerant expert tool, refrigerant replacement, so retrofits here. Here's pressure temperature charts for air conditioning. You can blow it up. You can put it on your wall. You got little PT charts here. They're in color. Here's one for refrigeration. Safety data sheet. There's also a guide for piping. I just shared it with the class this morning here, which the folks at this distributor were all getting giddy about, which I would too. It's pretty cool. Bobby Dean, shout out to Bobby Dean. He took what was old at one time, the old DuPont piping sizing chart, and I input a little bit on some trapping things that I knew from an article I wrote, and it's really, really cool. It's all kinds of graphs, man. Go to the website, check this out, www.optian.com training, okay, or optian.com training. One way or the other will get you there. All kinds of stuff now. The team that does all the work, the heavy lifting, the Shelleys, the Chris's, the Nikki's, and Nikki's team and what have you, they're really making this look really cool. It's a one-stop shop, if you will. So instead of going all these different links to a YouTube channel and all this stuff, you can come here and get all the resources you're used to, the data sheets for every refrigerant you're looking at, sizing charts, all that good stuff. And you can also see real videos. Dr. Chuck, who is the reason I'm here today, actually, he's the one that approached me about taking this position. He's in his 4th season, I believe, 4th or 5th season, and he does these little check up with Dr. Chuck videos. They're about 4 minutes long, and it's basically little chunks, easy to digest, little things we talked about today. Okay, it's nice, quick. So if you want to go in there and look up a topic and say, hey, what's an HFO or anything like that, Dr. Chuck has it for you. We're also recording these videos that we're doing right now for you. So within 24 hours, these videos go live to our YouTube channel. But you can get to that YouTube channel through our website now, which, again, by everybody doing all the heavy lifting behind the scenes. We're also having now, just released last week, I believe, what they call the Chill Zone Minute. And that's 1-minute videos that we're doing just on, like, did you know, fun facts, real quick, less than a minute long, real easy to digest on topping off refrigerants, you know, Glide, POE oils, whatever, just about A2L refrigerants. Again, those just got released last week, and they are on the website. I saw them already on there. They just got approved, and those are on there now too. So if you don't see something on there you like, I'm not sure we can make it happen. I hope I don't overstep my boundaries here, but suggest something too. You can always suggest. We're open for ideas. This is a live, active webinar. It's changing all the time, and believe me, it's really, really nice. And I mean that sincerely. It's come a long way. So let's open it up to Q&A.
Awesome. Thank you very much, Don. I appreciate all the content. Good stuff. We've got, let's see, we've got one good question and one good comment here from Mr. Barry Kepner regarding the curve charts. You were talking about that and talking about, you know, back-use and walkie-talkies. Barry Kepner says, Don, we still use these curve charts today, almost every day.
I know Barry. He's a friend of mine,
Oh,
Barry.
yeah.
Yes, you do. I wasn't trying to say we were old, Barry. Yes, they are used all the time. And you can find that particular code. I'll give Copeland a little shout out. You can find that on their Copeland mobile app too. So yeah, you are right. They're still out there. We used to call them curve charts, but what I was trying to say, Barry, is they're called performance charts. They put a fancy name on them. So what we used to refer to as curve charts, Copeland now refers to, and maybe that's a Copeland thing, refers to them as performance charts. So, but you are right. You do still use them.
Nice.
Yeah, very good.
And then we do have a question from Nadia Kamchuk, and her question is, hi, can we braze with 454B?
Oh, that's a great question. You know, hey, that sounds like an episode.
Yeah.
So yes, you can. You can compress fittings like we've been doing before, and you can braze. The difference here, and this is for another episode, we haven't really, I think we touched on this a little bit. So going back to ASHRAE 15.2 and 15, that's the ASHRAE makes the rules for installation. That's you and I, if you will, or when I was in the field. UL is the safety of the equipment. So UL, what they're saying right now is, and ASHRAE also is, a lot of things that used to be good practice is now going to be required. One of those things that's going to be required now, don't ask me who's going to police it because I don't know. I'm just the messenger. But it's always been good practice when you cut open a refrigerant line that you hook up your nitrogen, and that's why that purge setting's on your regulator, on your tank, by the way. That's what it is specifically for. You're purging that line out to remove any residual refrigerant. If you didn't know that, you probably already knew that, but not everybody does. Okay, so that's always been good practice. You remember me showing you that flame earlier of the A1? You know, when we get in there and we start repairing things, which I've done hundreds of times over and over and over, you see that little flame there, that little lazy candle looking flame, if you will, that's residual A1 refrigerant. That's 410A. That's anything you're using, okay? We think that's oil, but it's not. So now that the fact that even though this is almost mirrors what we're using today, now what used to be recommended or good practice is now going to be required. Again, I don't know how they're going to document that, but as fast as we are moving in technology with QR codes and everything and building departments, you may have to prove it. You know, you may have to somehow stamp off on it, you know. So, but yeah, that's a great question. You're still can braze with it. You can still use compressed fittings. You know, always as it was, and I know this is common sense, we're never going to put connections in a wall somewhere where you can't have access to it. And that's pretty much common sense. But people still do it sometimes. I've had to take siding off of houses before to find leaks and things like that. So yes, great question. I appreciate that. That was awesome.
Good deal. Thanks a lot, Don. And that's it actually that we have for the questions. We are also a couple minutes past the top of the hour. So let's see. If there are no other questions coming in, then we can close her down today and say goodbye for the next month. But let's see, I'm just waiting to see if there's anything jumping on in. Hey, Don, maybe you could tell us what's coming up for next month? I've forgotten.
Yeah, so yeah, that's awesome. Yeah, so next month we are having Bobby Dean from Tech Support, I believe, if I'm not mistaken. Nikki, if you're on the line, holler in, chime in here. We have our 6 months worth of class. I don't know if that's something we want to shoot out to everybody in advance or not, but anyways, we have already got 6 months already logged in, okay?
Nice.
And one of those months, I know for sure, we're going to start having some OEMs on. In fact, the gentleman I'm working with today from HTPG, which is the coil manufacturers on the refrigeration side, he's actually going to join us for an episode or two down the road, but it is coming up maybe in June or something like that. But yeah, I believe Bobby Dean, our tech support, was going to go in this month, but it wasn't quite dialed in like Bobby Dean and I wanted to. It's finished basically, but that was what was supposed to go in this month, but we backed it up a little bit because we really wanted it to be top notch. So we're going to go over like tech support questions, the most commonly questions that come in on the tech support lines. So we're kind of interested to see, are you getting those same questions? Do your questions match up, your top 5 match up with what we're seeing at headquarters? So that's it, Chris.
Nice, very cool. Yeah, that's going to be a good show. All righty. Well, we have no new questions, so let's wrap it up. Don, thank you again for all your content and all your help and all your information, and everybody who attended. Thank you very much for jumping on. We know you've got other places to be for this hour of your day, so we appreciate your time.
Thanks, everyone. Thanks, Chris.
Thanks, guys. See ya.